Okay, hello guys, welcome back. So this is the second video on career concern. So here we are looking at some sort of game theory model, right? So it's a little bit different from contract theory, in which we focus on the optimal contract. In contract theory, we usually try to characterize the optimal contract that serves two purposes. One is positive, the other is normative. So it helps understand the real world phenomena, why we observe certain form of contract in reality, that contract theory models help explain why we observe such things. And the other purpose is normative. So we want to make a better contract. We want to build better institutions, better society. So the meaning of characterizing optimal contract is twofold. But here we are not trying to characterize the optimal contract. We just want to understand why in reality strong incentive schemes, strong incentive contracts are not used ubiquitously. Sometimes we just observe very crude incentive scheme, and sometimes we observe wage contract, which is not which is basically fixed wage contract. So in previous one of the previous lectures, I explained why that is the case. So the theme is the strong versus balanced incentive, right? So in multitasking lecture, I explained in some situations, like one individual are supposed to do multiple tasks, then maybe we want to give weak incentive for all tasks, right? Because if you want to emphasize one task too much, then maybe that individual just do that task and giving too little effort on the other task. So that's one explanation. And here another explanation is if a worker concerns his or her career, then maybe that sort of strong incentive or direct monetary incentive is not necessary. So that's the theme. That's a theme that I want to discuss in this discussion, and I also want to say a few things, like today I can finish this, and then I don't know what I will teach next time, because we are ahead of our schedule. Usually, I mean in previous semesters, I could barely finish this discussion. So but here in this semester, I think we are quite ahead of schedule. So I don't spend much time explaining same thing repeatedly. I just explain one thing just once, and if you do not understand some part, then you can just go back to the previous videos and you can watch it again. So I don't need to explain many things over and over again. So that's one reason why we are ahead of schedule, and probably there are other reasons, like I don't answer to questions, and we didn't have midterm exams. There are probably lots of other reasons. Anyway, so we are ahead of schedule. So yeah, I don't know what I will teach next time, but I'll figure it out. Anyway, so another thing I want to say before we move on is we are using a new equilibrium concept, which is sequential equilibrium here, right? So the sequential equilibrium has two elements, two requirements. One is on belief, the other is on strategy. So the belief must be consistent with the strategy, and strategy must be optimal given the belief. So we want to impose two things, right? Two requirements. So we first describe the belief system, how the beliefs are updated, right? So that's the first thing we want to do. And then later, given this belief updating rule, we want to characterize the optimal strategy, optimal effort decision. So that's what we want to do. So here there are several differences from the previous models. Here there is asymmetric information about talent and also about effort. And so the output or the performance or the revenue YT is sum of talent plus effort plus some noise or luck, right? So that's one difference. And another difference is this is repeated interaction. In previous models, we just consider one-shot model, which means we just the workers, the worker and the employer interacts only once. It's just one-shot game. But here we are looking at a repeated interaction. So when you decide how much effort to put, you have to think about the effect in the future, right? So that's another difference. And also, lastly, a big difference is here we assume there are many potential employers and they compete to hire this one particular worker. So the labor market is competitive. So that's the difference. So I introduced the model last time, so I just want to just quickly review what we have done. So MT is the expected level of talent, and AT star is the equilibrium effort level, and we'll just use these properties of normal random variables, and given this normality of random variables, the conditional expectation and conditional precision can be written like this. Conditional expectation, the expectation of X conditional on S is the signal, is basically the weighted average of two numbers. One is prior belief or prior expectation, which is M, and the other is new information, the signal S. So it's the weighted average of these two numbers. That's the conditional expectation of X. And conditional precision is that the new precision, updated precision, is the sum of prior precision or previous precision H plus H epsilon. H epsilon is the value of new information, the precision of new information. Right, so we'll just use these properties to describe the evolution of the belief. So the new belief on talent, MT plus 1, is expected value of eta. Eta is talent, so that's what we want to know. And the information given at that period is Y1 to YT. So but the information on information in Y1 to YT minus 1 is encapsulated in MT. So in other words, MT is sort of sufficient statistic of Y1 to YT minus 1. So it encapsulates all necessary information about the or sufficient information about Y1 to YT minus 1. Okay, so MT plus 1 that's the belief about eta, which is held in period T plus 1, and that is the weighted average of two numbers. One is the prior belief, MT, and the other is the new information, YT minus AT star. So I explained why we use YT minus AT star instead of YT itself, because YT is sum of eta plus AT plus epsilon. So what we want to figure out is eta. So to figure out that we subtract AT from YT. Okay, so that's the new information. So the new belief, updated belief, is the weighted average of two numbers, MT, and the new information yt minus at star. And updated precision ht plus 1 is ht plus h epsilon. So these are mathematically driven. We just use these properties, but I just want to emphasize that this is not some made-up formula. This is correct mathematical formula on conditional expectation and conditional precision, given the assumption of normality of random variables. Okay. So here we define zt, which is yt minus at star, which is also can be written like eta plus epsilon. And at star is the equilibrium effort level, and ht plus 1 is h1 plus t times h epsilon, and what that means is as t goes to infinity, ht plus 1 goes to infinity. So what that means is eta is revealed almost surely, which means the probability that this ht plus 1, the difference between ht plus 1 and the difference between eta and mt plus 1 goes to 0 as t goes to infinity. Sorry, what did I say? Let me try it again. So the probability that the difference between eta and mt plus 1 is larger than certain number goes to 0 as t goes to infinity, whatever that number is. So that's the definition of it's revealed almost surely. It's statistically well-defined terms. It is well-defined term in statistics. And mt plus 1 can be written like this. So mt plus 1 can be written as a function of m1 and h1. m1 and h1 are some known numbers, right? So m1. So let me go back to that slide. So here the worker's talent eta follows normal distribution with mean m1 and the standard deviation sigma 1, right? So that's the definition. So we, from the beginning we know what m1 is, and of course we know what h1 is. They are some known numbers. They are given from the beginning. Okay. So mt plus 1 can be written as some functions which are functions of some known numbers and some new information. So zs is the new information, right? So it can be written like this, and more generally it can be written like mt plus s equals to mt times ht plus h epsilon times sum of zr over ht plus s times h epsilon. So I start today's lecture by explaining how we get this formula. Okay, so mt plus 1 equals to ht plus mt. Sorry, there is typo here. Okay, maybe I should stop here or okay, let me just move on. So the formula is not correct. There is typo here. So at the top, mt plus 1 equals to h1 times m1 plus h epsilon times zt over ht plus h epsilon. Sorry. Yeah, that is also okay. Okay, yeah. So this is fine. Sorry about that. So okay, there is nothing wrong with this formula. I apologize. There is nothing wrong in this formula. I was just mistaken. Okay, so mt plus 1 is the weighted average of MT and ZT. Okay, so MT is the prior belief and ZT is the new information, new signal, right? So, and the new belief is weighted average of these two numbers. And using this, we can derive the formula at the bottom, right? So that's what I want to show, right? Okay, so we want to derive the formula at the bottom from the formula at the top. How do you do that? First, we multiply ht plus 1 on both sides. Okay, so multiply ht plus 1. So the denominator on the right hand side of the formula is ht plus 1, right? So let me go back to this slide or this slide. Okay, here ht plus 1 equals to ht plus h epsilon. So ht plus h epsilon is ht plus 1. So we multiply, so we are looking at the formula at the top. So we multiply ht plus 1 on both sides. Then we have on the left hand side we have ht plus 1 times mt plus 1, and on the right hand side we have the number. We have the expression in numerator, right? And then the next step is we use this formula to ht times mt. Okay, so what is ht times mt? Ht times mt is ht minus 1 times mt minus 1 plus h epsilon times zt minus 1. That is ht times mt. Okay, so we just reapply the formula in the second line. So look at the formula in the second line. We reapply that formula into ht times mt. How do we do that? So we move the time one step back. Then we have ht times mt equals to ht minus 1 times mt minus 1 times plus h epsilon times zt minus 1. So we just plug that in to ht times mt, and we do that again and again, and eventually we'll have the formula at the bottom, right? So the h1 times m1 plus h epsilon times sum of zs. Okay, so that's what we have, and that is what at the very left of this formula we have ht plus 1 times mt plus 1, and now we divide both sides by ht plus 1. Then we have the formula at the bottom, very bottom, right? We have the formula at the very bottom. So then we have the mt plus 1 on the left hand side, and on the right hand side we have this expression, m1 times h1 plus h epsilon times sum of zs over h1 plus t times h epsilon. So at the denominator we have h1 plus t times h epsilon. That is nothing but it is nothing but ht plus 1, right? So that's how we derive this. Okay, and so that's the end of one discussion. What is it about? It is about the evolution of the belief. Okay, so it describes how the belief is updated. So finally we got the formula like mt plus 1 or mt plus s as function of some known numbers and realized value of yt or z, right? So that describes how the belief system, the belief is updated. And we move on to the next discussion, which is about the strategy, right? So the belief must be consistent with the strategy, and the strategy must be optimal given the belief system. So now we are talking about the strategy. So given the expectation on the sequence of equilibrium effort AT star, the worker's expected payoff can be written like this. So the formula on the the first formula is the expected utility of the agent. It's basically same with this, the expression at the bottom. So the agent's payoff is the discounted sum of instantaneous utility. Instantaneous utility is the utility that this worker enjoys in one period, right? So that is WT minus C of AT. So that's wage minus effort cost. So it's basically this expression, but here, okay, so again, so it's basically the same expression, but it looks a little bit different because I took the instantaneous utility in period T out from the summation, and and in the summation we have the instantaneous utility or expected utility from T plus 1, period T plus 1 and on, right? So by separating these two, I want to emphasize that on the left hand, on the left at period T, we have expression like AT, right? So the effort, so the choice variable here in period T is AT. But at the very last term, at the very right, the last term is C of AT plus S star. So there is star on the AT plus S, but there is no star in AT. So the difference is AT plus S star is the equilibrium effort. So there is some known number. So everybody knows equilibrium strategy. So everybody have some notion about equilibrium. So and people, the participants of the market knows that value, knows that number. So these AT plus S star are not choice variables. They are some known numbers. The idea is this: in period T, I decide AT. I decide how much effort to put today. And tomorrow, I will decide how much effort to put, right? And the day after tomorrow, I will decide something else. Okay, so the point is, what will happen in tomorrow will be determined tomorrow. My choice variable today is AT. I do not determine, I do not choose AT plus 1 or AT plus 2 or all the other effort levels in the future. What I can choose now is today's effort level. Okay, that's the point. So I just have some expectation about future, and everybody has some expectation about future, the future effort level, and but what I can do now is I can decide my effort level. Okay, so that's the choice variable. I can choose only one effort level, which is today's effort level, AT. That's why we have AT and AT plus S star. So you know what I mean. So the star is the equilibrium effort level, AT is the choice variable. And I want to I want to maximize this expression by choosing the right A, right AT, okay, right effort level today. But it looks a little bit messy, so I want to simplify this expression like in the bottom. Okay, so this is basically the same problem. So maximizing the expected payoff of the agent is same with the maximizing the expression at the bottom. How is so? Because first I dropped WT, the very first term WT is already determined. So it is already determined. So it's a constant. So it is not affected by my effort level today. So it is already determined that I get certain amount of money. My effort will not affect that wage. So I can drop a constant from this objective function. So I drop WT. And I also dropped the future effort cost. Okay, future effort cost is C of AT plus S star. C of AT plus S star, that is future effort cost, and there is nothing I can do about that. It will be determined in the future. If I work hard, still if I want to work hard tomorrow, then the cost will be borne in the future. And if I do not like to work hard, then in the future my future self can determine low level of determine to put low level of effort. So that's something to be determined in the future. So from now, from now's point of view, from today's point of view, the cost function in the future, the effort cost in the future is basically constant. There's nothing I can do. I cannot influence that effort cost in the future. So I can drop it because it is constant. And what's left is the wage, right? So in WT plus S, so let's look at this wage in the future. WT plus S is MT plus S plus AT plus S. Let me go back to this. Okay, so look at this. WT equals MT plus AT star. Okay, that is derived from the assumption of competitive labor market. So in competitive labor market, the expected profit must be zero. So zero profit condition leads to this wage level. The WT equals to MT plus AT star. So going back to this slide. So WT plus S is MT plus S plus AT plus S star. And what did I say about AT plus S star? It is equilibrium effort level, so it is some known number, and the that effort level will be determined in the future. So there is nothing I can do right now. So in other words, they are constant numbers. So I can drop it. And what's left is simply this: the effort cost today plus the future belief about my talent. Okay, so what that means is, if I work hard, if I put more effort, if I put higher effort today, then my performance, the revenue will be higher, right? So YT will be higher. If I put more effort today, then YT will be higher, and that will give that will give a positive effect on the future beliefs about my talent. Okay, so that's why I work hard today, right? So if I work hard today, then the market will believe that I'm talented, I'm productive. So what I want to do today is I want to give a better impression to the market. So the market believes that I'm a productive worker, and that will have a lasting impact on my wage because the market believes that okay, this worker is productive, this worker is talented, and that will give a lasting impact on my wage, my future wage. Okay, and but to write down the exact expression for the equilibrium effort, we want to work on this a little bit more. So first, what is MT plus S? Expected value of MT plus S. MT plus S is the belief held by the market in period T plus S about my talent, right? So that's MT plus S, and that can be written like this. That is MT plus H epsilon over HT plus S times H epsilon times AT minus AT star. Okay, so that's the expression. And how do you get this? We use this formula, right? So MT plus S equals to MT times HT plus H epsilon times sum of ZR over HT plus S times H epsilon. We use this formula. This formula is this is not derived exactly, but something very similar has been derived in this slide. So here, instead of look at the bottom formula. So here, instead of 1, we can put S. Sorry, there is S here again, but this formula can be this formula is very similar. It is basically the same formula, similar to this formula, the second formula, right? So the MT plus S equals to MT times HT plus H epsilon times sum of ZR over HT plus S times H epsilon. So we want to use this formula to get a better expression, more manipulatable expression. First, what we want to do is we want to understand what ZR is. We want to modify this expression. This what is the expected value of ZR at period T. So look at the formula at the bottom. So we put expectation on ZR. So ZR is the definition of ZR is YR minus AR star. So that's the definition of ZR. And yeah, so at the very first line, I repeat that. So expected value of ZR is expected value of YR minus AR star, and that can be written like this. So first, I separate the expression and period T and the thing in the future. So in period T, it is YT minus AT star, and in the future it is just YR minus YR star. The reason why I separate these two is this. In the third line, look at the third line. In the third line, in YT, we have AT. But in YR, the future Y contains only AR star. YR contains AR star, but YT contains AT. So AT is something to be determined now by myself, right? So today I'm going to determine AT. I will determine how hard I will work on this task. So that's what I will do today. So that's something to be determined by now, by myself. Okay, so we have AT in YT, but we have AR star in YR, right? You can you see the difference? So in YR, so R is some day in the future. So you just have some expectation about YR, and you have some expectation about AR star. You just believe that maybe in the future I'll just follow equilibrium strategy, but there's nothing you can do now, right? Because the future effort will be determined in the future. So that you just have expectation, and your expectation is that you will follow that equilibrium strategy. So that's why you have AR star. Okay. But today you can determine AT. So what we'll do next is you just that was the difficult part, and what we'll do next is you just rewrite the formula. This just algebra, right? So expected value of eta is mt, and you have expression like AT minus AT star, and right, so expected value of eta is mt, and there is summation over it. So there are s minus 1 mt's. So the expression is eventually it boils down to the expression at the bottom. So it's s times mt plus at minus at star. Okay? Remember this expression for a moment. Remember this expression at the bottom. S times mt plus at minus at star. And we plug this into the sum of ZR. In the second line, we have sum of ZR, and we plug S times MT minus plus AT minus AT star in there. Okay, and then eventually so you can look at this instead. So expected value of MT plus S, so that's the basically expected value of eta. Okay, expected value of eta. So currently you have certain information and you don't know what you will observe in the future, but you can just imagine, and in the future something happens, and maybe eventually the belief about eta will be mt plus s, but we don't know what that is. So we just form some expectation about future expectation. So this is what it is. Okay, so expected value of mt plus s is basically the expectation about expectation in the future. So it can be written like this: mt plus ht plus h epsilon times sum of expected value of zr, but according to what we just derived, sum of expected value of zr is s times mt plus at minus at star. So after doing some algebra, we have this expression: mt plus h epsilon over ht plus s times h epsilon times at minus at star. And then finally we can rewrite the agent problem like this. So here we have this expression, and then finally we have this expression. So the what I just did is look at the expression at the bottom. Here we have expected value of mt plus s, and there we have what? mt, right? We have mt, and mt is a given number in period t, so it's constant. You can just drop it, and what's left is basically this. First, you have effort cost. When you decide the effort level, you have to consider the effort cost, And then what do you have? You have the effect of effort in the future. So if you work hard today, then in the future the market will believe that you are productive, you are talented, and that effect is captured. It is expressed in the in this formula. You know, it has a lasting impact on the future belief. So we have this summation over 1 to infinity, and the effect can be written like this. So you can solve this problem, right? You differentiate this objective function with respect to at, then you have the first order condition at the bottom. So the first order condition is the marginal cost equals to the marginal benefit on the left hand side. The right hand side. So the left hand side you have the marginal cost. On the right hand side you have the marginal benefit of working hard today. So this gives the equilibrium effort. Okay, so just to be a little bit more concrete, let's assume that the cost function is quadratic. Okay, so the cost function is half times at star. Then you can say that at star is sum of beta to the s times h epsilon over ht plus s times h epsilon. Okay, so that's the equilibrium strategy given the belief updating rule. So to derive the belief updating rule, we assume that at star is some known number, and everybody knows what the equilibrium effort level is. And in equilibrium, the worker follows the equilibrium strategy. So at star is some known number, and that was the assumption when we derived the evolution of belief system. And then given the belief updating rule, we just derived the equilibrium effort level or the optimal effort level. Okay, so that's the sequential equilibrium, right? The sequential equilibrium is the belief which is consistent with the strategy, and the strategy which is optimal given the belief. So this is it. And from this, we try to understand the properties of the equilibrium effort. The first is this: the at star does not depend on the realized value of yt. So we assumed that we guessed that the at star is some known number, so it doesn't depend on the realized value of yt, and it turned out that is indeed the case. Okay, so it's this method, guess and verify method works, right? So we guessed at first that at star is some known number. At stars are a sequence of known numbers. Okay, they don't depend on the realized value of yt, and it turns out that that is indeed the case. They don't depend on the realized value of yt, so they are just some known numbers, sum of some known numbers, beta, h epsilon, ht, s, everything is known number. And another observation is this: at star decreases to 0 as t goes to infinity. As time goes by, the equilibrium effort level goes down to 0. Okay, you can see that from this expression. The at star has ht at the denominator, right? So ht, you have ht at the denominator, and ht goes to infinity as t goes to infinity, right? We can go back to this slide, right? So the ht plus 1 goes to infinity as t goes to infinity. So going back to this. So what that means is the equilibrium effort level goes to 0 as t goes to infinity. Why is that? Because as t goes to infinity, the market has very strong belief, the stronger belief, right? So the market observes the performance of the worker over time, right? So after a long time, the market realized that, okay, we have observed this worker enough, so we have very confident belief about this worker's talent, and maybe in the future we'll observe more YTs, but that will not change our belief much because we have already observed too much. We have already observed enough. So as you observe more performance, as you get more signals about the talent of the worker, your belief about the talent of the worker gets stronger over time, and eventually that belief is so strong that new information will not change that belief held by the market. So the belief is already strong, the market is already confident about your talent, then there is no reason for you to work hard, because you cannot change the belief of the market in the future. So you just don't work hard. Okay, that's why the equilibrium effort level shrinks down to 0 as t goes to infinity. Okay, and you can say similar thing about H1. So if H1 is infinity, H1 is the precision held by the market, so or the confidence held by confidence of the market in the beginning. So H1 equals to infinity means that sigma 1, the standard deviation of the belief on the talent, is 0. The standard deviation equals to 0 means that the market basically knows the talent of the worker from the beginning. Okay, so in other words, there is no imperfect information problem. Then AT star equals to 0 for all t. So if there is no imperfect information problem, then the worker has no incentive to work. The worker works hard because the worker wants to signal to the market. The worker wants to send some signal to the market about the talent of the worker. So that gives the incentive to work. But if there is no asymmetric there is no imperfect information problem about the talent of the worker, then worker has no reason to work hard. Okay. And the second bullet point, as beta goes to 1, that means as the worker becomes very patient, AT star increases. So what that means is the worker who concerns his or her career more will work harder. And as H epsilon goes to infinity, AT star increases. One can send more informative signal, then the worker will try to send a better signal. Okay, and there is some sort of red race. What that means is working hard does not result in a better belief. This is a little bit misleading expression, but what I want to say is the market has some belief about your equilibrium effort, and you're basically in a race with that equilibrium strategy. And if you work hard, if you just do the equilibrium strategy, if you just choose AT star, what I mean is AT equals to AT star, then you work hard, but the belief will just follow the equilibrium belief path. You don't make a better belief. But you still have to work hard, because if you do not work hard, then the market will believe that your eta is very low. So just to keep up the belief, you have to work hard. That's what I mean by red race. Just to keep up the belief, so the market will discount your performance using this 80 star. So if you do not work hard, then the market will believe that, okay, this guy is not talented, this guy is not productive. Okay, so that's a sort of tragedy. Okay, yeah, so that's pretty much it. So we consider the situation where a worker stays in a labor market for more than one period, so there is repeated interaction. So the worker try to send a good signal to the market, and the possibility of being hired at a better salary gives the worker an incentive to work. And there is some policy implication of this model, which is this. A young worker who concerns his or her career may not have to be given direct monetary incentives, but for old workers, direct incentives are important, and that's consistent. This idea is consistent with what we observe in reality. In junior years, in firms, you are not given you're not given much direct incentive, but as a senior in the firm, maybe you will be given a better incentive, monetary incentives. And the reason is, young workers concern the future, they concern the career of himself or herself, so the direct incentive is less necessary. But for old workers who do not care much about the career, the market already observed the performance of the worker enough, the direct incentive is more important. If direct incentive is not given to old workers, then these old workers will not work hard. So the incentive to send signal to the market is weak for these old workers. So for old workers, direct incentives are important. Okay, so that's some sort of policy implication. Okay, so that's it for today, and see you next time.